This is Unit 6, Lesson 7, Part 2. So we're picking up kind of in the middle of these notes where we left off with the last lesson. So the first thing we're going to be doing is verifying inverses, and it's going to be tracing back to something we did before with composition of functions. So this should look familiar. So we are working with functions f and g. So they could give you two functions if you look kind of below at these examples. We could give you two functions and ask you to prove whether they are or are not inverses of each other. So here's our definition. If f composed with g of x comes out just exactly to equal to x, like you plug g into f, you simplify it, and it comes out to just equal x exactly, and you do it the other way, f composed with g, meaning you plug f into g, and that also comes out to exactly equal x, that means they're inverses. So I'll show you what that means. We're going to do 12 and 13 on this page. Our instructions are to determine whether the pair of functions are inverse functions. So we're going to start with this first direction of composition. We're going to start with f of g of x. So remember what that means is we are taking our function g and plugging it into our function f. So we are taking this function right here and plugging it in where there's an x. So x squared becomes this squared. So x squared and then plus 8. So plus 8 after. So we are simplifying this down. We're going to see what it becomes. So first thing we notice is that you've got a big square root and then you square it. So those two things will cancel and you just have x minus 8 from this part and then plus 8 at the end. So minus 8 plus 8 and all we end up with is the x, which is what we were thinking would hopefully happen if they are inverses. So that's a good sign. We have to do it the other way as well and confirm. So now we do the other composition, g of f of x, meaning we take our function f and plug it into our function g. So we are taking this function right here and plugging it in where there's an x. So our function g is square root and then x minus 8, we plug in x squared plus 8 and then minus 8. So this replaced the x that we had here. So simplify this up. Under the square root, the plus 8 minus 8 will cancel. So then it's just an x squared. And the square root and the squared cancel, so it is just an x. So when I compose this way, it came out to be x as well. So we can say that yes, they are inverses. So now let's check another example. We've got f of x and g of x. So we're going to start with our first direction of this composition. F composed with g means we're taking our function g and plugging it into our function f. So this x right here. So we have negative 4x. We're going to replace that with this whole function. And then after that, we have a plus 5. So simplify this up. First thing I'm going to do is distribute this negative 4. So distribute the negative 4 here, and we have negative 4 over 4, which is a negative 1 times x. And then negative 4 times negative 5 would be plus 20, and then plus 5. So simplify this up, we get a negative x plus 25, which means this is not what it's supposed to be. So if this happens, there's absolutely no point in checking this one because it both has to be true. It says and, capitalized, it's bolded, they both have to be true in order to be inverses. So if even one of them is not true, there's literally no point in checking the other one. So we would say that no, they are not inverses. Don't even need to check the other one. But if the first one works out, you do have to check the second one to make sure that they both work. So that's our first type of problem that we're going to be looking at, is determining whether these pairs are inverses. On the next page, we're going to be looking at graphing inverse functions. So it starts off with this triangle that is formed with these 3 different points. So it gives us ordered pairs, and we're going to plot those. So we can plot negative 1, 6. So negative 1, 3, 6 right here. Negative 7 and 2 right there. Negative 5, negative 3 right there. So it says it's a triangle that is formed by these 3 points. So I'm going to connect the dots, just show you that it is in fact a triangle. Looks like that. So letter A first says, what is the inverse of this relation? So we did this a handful of times in the previous lesson. You just take these ordered pairs and just flip them. So first ordered pair, negative 1, 6 becomes 6, negative 1. Negative 7, 2 becomes 2, negative 7. Remember, you're not changing any signs. You're just literally flipping x and y. And then negative 5, negative 3 becomes negative 3, negative 5. So we're going to plot those 3. letter B tells us to graph ABC, which I guess we did a little early, and its inverse. So we're going to plot this as well. So plot 6, -1, B2, 4, 6, -1, 2, -7, and -3, -5. Right there. So connect the dots, we get another triangle. This is the inverse triangle. Looks like that. And so what do you notice about the graphs? You might not notice it immediately, but I want to show you something kind of cool. There's this line that runs diagonally, kind of like at a 45-degree angle down here. And this is the line y equals x. So every point on this line has a y value and an x value that are the exact same. It's like 0, 0, 1, 1, 2, 2, 3, 3. Every x and y value are the same on this line. So with an inverse, because you swap the x and y coordinates, what ends up happening is like over here, you have the point, you know, -2, +2, but over here you have the point +2, -2. So when you swap the x and y points, what ends up happening is you get this symmetry over this dotted line. Okay, so it is reflected across the line y equals x. And that's this like perfect diagonal line that goes right down the middle. Think of it as having a slope of 1 and a y-intercept of 0. So this is something that's going to be true about all inverse functions. So we can look at a couple right here. We'll start with number 1. First says find the inverse of each function, which is a little flashback to video part 1. So the first step is we, instead of f of x, we write y. Second step is you exchange the x and y like this. Third step is you get the y by itself. You solve for y. So I'm going to do that by subtracting 8 from both sides. And then, whoops, don't forget that. And then I have to divide by that 2. So divide everything by 2. So dividing 1 by 2 becomes a 1/2 in front of the x. Dividing -8 by 2 becomes a -4. And then the y is by itself. So then as a very last step, we write it in this inverse notation. So that's our inverse function. So that was step 1. Then graph both functions and verify the inverse relationship. So we're going to graph this. Little flashback to, I think, unit 1 when we were graphing equations like this. So 2x plus 8. So we start with a y-intercept up here at 8, and then we have a slope of 2. So we can go up 2 to the right 1, and then we run out of space. So let's reverse and go down 2 into the left 1. And we're just going to keep doing that. Down 2 into the left 1. It's going to take up a whole bunch of space on our graph here until we reach the end. So that is our first line. That's the original. So this is just f. And this is our inverse function. So start with our y-intercept at -4, which is right here. And then our slope is 1/2. So we go up 1 to the right 2, up 1 to the right 2, carry that pattern out until we run out of space, and then go back in the other direction. Go down and to the left, down 1 to the left 2, and carry that pattern until we run out of space. So this graph will look like this. So this is f inverse. So now verify the inverse relationship. That means we want to look at this dotted line right down the middle and just kind of confirm visually that it is a match, that you can see these things going on both sides. So I'm going to use, I don't know if this pink will show up. We'll see. Yeah, you can see that. So if you look, you can see that you've got this symmetry, and it even helps if I look at it that way. So you see this little like kite shape, that the shape that you have over here is like a perfect mirror image of what you have over here. And that is a visual confirmation that they are in fact inverses of each other. All right, we're going to do one more. We'll do number 3. Number 3, we have f of x equals x squared minus 4. So first thing is we write a y instead. Second thing is we exchange x and y. Third thing is that we solve for y. So I'm going to start by adding 4 to both sides. And then I will take the square root of both sides. So square root both sides. Now this part's a little bit tricky because when you do take a square root, you have to make sure that you have a plus or minus. So we're going to flash back to a few lessons ago when we graphed square roots so we can plot the original and its inverse. So this one, this is a parabola. This minus 4 means it moves down 4 units. All right, so we go down 4 units, graph it right here. And then the parabola, normal x squared, just goes like up 1 over 1, up 1 over 1 in both directions. So that's like, we just kind of want to see what that parabola is going to look like, and that's enough to just give a quick sketch. So our parabola looks like this. Square root, remember what this means, x plus 4 means you move to the left 4 units. So we start at the origin, but then we move to the left 4 units, which starts it off right here. And then we had this pattern that we followed that was like up 1 to the right 1, up 1 to the right 3. So we go up 1 to the right 1, up 1 to the right 3, and that's probably enough. So this is the positive square root, looks like this. And then the negative square root is the upside down version. So instead of going up, we go down. So this one goes down 1 to the right 1, down 1 to the right 3. And again, that's probably enough to see what this shape is going to look like. So you can see that square root. So then our kind of visual confirmation, just put this line down the middle so you can see that you've got these like this crazy symmetry, these mirror images of each other from the parabola compared to that double square root function.